All right. So last time, we talked about what a group is. And a group is just, it's a non-empty set, and you've just got a way to combine any two elements of this group and get a new element of the group. That's all there is to it. Now, the way to combine it has to solve, has to satisfy a couple rules. So we don't want things to get all out of hand. It's got to be an associative, right? G1 combined with G2, G3. The G1 combined with G2 combined with G3. But also, we assume there's this magic element called the identity in the group, such that when you combine it with G, you always get G. It sort of leaves it alone. Sometimes it's called a neutral element. And for all G and G, there's H and G such that when you put G and H together in either order, you get the identity. So how about some examples? Well, let me get this. Well, so now on, I will probably, I put this dot in here for dramatic purposes. From here on out, I will probably use juxtaposition. So I'll just omit the circle. We say G is abelian if for all x, y, G, x, y.
We're just trying to
So,
bring that.
In other words, it doesn't matter what order you try to put together, you get the same result. Okay, so how about some examples? Let's develop some examples of groups. Oh, and I'm gonna have to think of this. Yeah. By this notation, I mean the order of G, that's the number of elements in G. So this is just like the set theory notation from 3190. This is just the elements in it. If G has a finite number of elements in it, we say, surprise, surprise, G is finite. Okay, so let's look at some examples of groups. This is the integers, and my operation, my binary operation is addition. This is a group. Well, what happens when I add two integers? I get an integer. Is addition of integers associative? Yes, otherwise we wouldn't be sitting here now. Math would be just too out of control. The neutral element, what can you add to any integer that leaves it alone? Zero. And what's the inverse of any integer? All right, so if I give you the integer n, its inverse is negative n. That's what you add to it to get back to zero. The additive inverse. Does it matter what order you add integers? No, you get the same answer. Triple stop stops. So are the rational numbers under addition. So are the real numbers under addition. So are the complex numbers under addition. These are all examples of a abelian group. Yes.
Does the inverse have to be unique? Or
What's
no?
that?
Does the inverse of an element have to be unique? Or no?
Great question. Yes, and we'll get to that in a moment. Yes, the inverse does have to be unique. These groups are all. Anybody give me an example? Well, let me ask this first. Is this a group? No, it's
No.
not. Well, let me ask you this. If I take two integers and multiply, what do I get? another integer. So far, so good, right? Is multiplication of integers associative? Yes, it is. Otherwise, we wouldn't be sitting here. How about the neutral element? What can I multiply by any integer and it leaves it alone? Ooh, man, this is better than meatloaf song because we got 3 out of 4 already. What about the last?
Not in enemies.
Give me an example of something that doesn't have an inverse. 2, right? That was more fun. I think. This is not a group because, for example, single inverter. There is no 1/2 in Z, right? So that's problematic for you. Okay. You stole my thunder a little bit, but I'll go with this. What about the rationalism? What about the rationalism? This will make you angry, right? Still not, but there's only one problem. Yeah.
0 is not inverse.
Right. Can you fix it? No, everything else works. Every other rational number has an inverse, right?
Q set minus 0.
There you go. Just throw out the 0. This isn't given. You can also replace that Q by the real numbers minus 0, like complex numbers minus 0. These are all examples of being improved. Still, everything is infinite. And everything is abelian. Can you give me an example of a group that is not abelian? So all of these groups, order doesn't matter. It doesn't matter if I multiply what order I multiply rational numbers or real numbers, they get the same answer. Anybody, do you think of a math class that you've had before where order multiplication didn't matter? Yes.
And you're optimal.
That's right. I seem to recall that if you have 2 by 2 matrices or bigger, you run into the trouble that sometimes A times B is not B times A, right? Two by 2 matrices with real numbers. Now, there are a couple ways I could think that you can combine 2 by 2 matrices. Tell me what they are. I can think of 2 ways to combine 2 by 2 matrices and still get a 2 by 2 matrix.
Multiplication and addition.
You can add, right? Does that form a group? Well, the answer is yes, right? Because when you add 2 by 2 matrices, you get a 2 by 2 matrix, right? Matrix addition is associative. You might have even shown that in 3110. What's the neutral matrix under addition? 0 matrix, right? You add that to any matrix and it's 1. And the inverse of a matrix under addition is you just reverse the sign in every component or in every coordinate, right? And in fact, it's appealing. But this violates the spirit of what I want. I want a non-abelian group. Is 2 by 2 matrices under multiplication a group? When you multiply 2 by 2 matrices, you get a 2 by 2 matrix. Okie dokie so far? Matrix multiplication is associative. Again, I appeal 3110 for that. What's the neutral matrix? The identity matrix, right? 1, 0, 0, 1, right? What about the last? Does every matrix have an inverse? Only the invertible one, right? And how do you tell that? What's the little key thing that you look at?
Non-zero.
Right. Does everybody remember that the matrices that have non-zero determinants are the invertible ones? So this is, there's too much here. So let's look at this group instead. This is a set of 2 by 2 matrices over R. Non-zero. This is a group under multiplication. Yes,
With GLP.
that's just the standard notation for this. It stands for general linear group. And that's. So it's 2 by 2 matrices with a non-zero determinant. This forms a group under multiplication, right? And it's. You've seen all this stuff in linear algebra, and the inverse is, of course, in fact, for 2 by 2s, you have a formula for the inverse. You'll remember that. It's something with like reversing the coordinates and divide by the determinant. Right? And it's not abelian. I'll have to get really unlucky. Not worked out. Let's see, that has non-zero determinant. And so does that. And I've looked at AB is equal to, what does it equal to? 1, 2, 1, 5. And the A is equal to 6. Well, I guess I can put it right there, can't I? Because I already know it's not equal, but let's go through it. 6, 3, minus 1, 0. And these are not equal. Yes,
Can you make them equal? Like if you set them equal right there, like you set an equivalence clause. Like you make an equivalence correlation.
So that's a little bit more complicated. So what you can do is, we're gonna get to stuff like that. But, you can't really formally make them equal. I mean, you could maybe declare some kind of equivalent class. And we'll get to those kind of constructions later, actually. Okay. Look at me, look at me. I've given you examples, groups, all kinds of them, under addition, under multiplication, lots of million ones. And of course, this generalizes to any size matrix n by n, right, that has non-zero determinant. Can anybody give me an example of a finite group? Every one of my examples has infinitely many elements in it. Yes.
You have the trivial group, which is just the set.
Oh, what a smart aleck he is. That's a great example, right? That is, I love the smart aleck. That's the easiest thing to think of. You've got the trivial group where you've only the identity, right? I mean, why would you want to study it? It's just one stupid thing in your head, but it's there. Right? Okay. Make it bigger.
You add another element.
Okay, right. Well, let's do that. Yes.
Would it be like the C sub some prime number?
You know, to me, that's kind of one of the best examples. So, and this is under addition. Remember how we did that kind of circular clock thing, right? So specifically, let's say C5. Remember how we added it up and it's just whatever you get when you add it up, but if you go bigger than 5, kind of cycle around, take the remainder. What happens when you add any 2 of these? It still ends up in that set because even if it gets bigger, it's just cycled back around in the set. Okay, so far. The addition is associative. the neutral element is 0 bar. Everybody agree with that? How about inverses? Well, so this is finite and small, so I'll give you kind of an explicit list. I'm gonna pair everything off with this inverse. The identity is its own inverse. What's the inverse of 1 bar? 4 bar. This is a pair of inverses. And this is. I'm gonna throw this one in there. This one's kind of interesting. You see a little bit of difference between the even and odd. This is its own inverse. The inverse of 1 is 5 here. The inverse of 2 bar is 4 bar. And the inverse of 3 bar is also itself. This is a finite. Abelian. Okay so far? Yes, sir.
So I said prime, but you've also shown that prime is not necessary.
The prime is not necessary.
Okay, so I think I'm.
Actually, there is something wonderful and magical about primes, but we're not to that yet. Because what happens with prime, so this is kind of the fun part. What happens with prime is it behaves just like this additive, like the 5, for example. But with primes, if you throw out 0, the non-zero elements form an abelian group under multiplication. Right, as a matter of fact. This does happen here because if you throw out 0, the inverse of 1 is itself. The inverse of 2 is 3. 2 times 3 is 6, which is 1. And the inverse of 4 is itself. 4 times 4 is 16, which is 1. Right? This doesn't happen here because it's not prime. 2 has no inverse because the problem with multiplication here is what's 2 times 3? 0. And that's a problem. But we'll, like I said, we'll get into more of that. Okay, I've got another one for it. Can anybody give me an example of a group that is both finite and not abelian? All right, so we've covered all the bases. We have infinite abelian, we have infinite non-abelian, and we have a finite abelian group. Yes.
I didn't think it's so perfect. Do matrices over a finite and reveal.
That's a great one, right? He said matrices over, if you have like, if you look at 2 by 2 matrices, non-zero determinant over, over a ZP. Let me give you one that's, I'm gonna give you a couple. I'm going to go through this example. This one's an important one because we're going to build on this. And actually, one can make the argument that if you understand all these generalization of S3, NESN, then you understand all of group theory in a certain sense. That's being a little bit facetious. How many bijective functions are there from 1, 2, 3, and 7? Yes,
6.
there are. How did you get that sometimes?
So it's just the first element can go 3 places, and then there's 2 places left for the second element, and there's only 1 place left for the first element. So it's 3 times 2 times 1.
We're going to study this generalization of this more extensively later. But I'm gonna, since there's only 6 of them, I'm gonna have to list it out. Now, he said there's 6 bijective functions, right? So here's the argument. Start with 1. How many places can one go if this is function?
Great.
It's got three possible choices. Now you make that choice. Now you gotta send two somewhere. How many choices you got now? Two, and then you make choices. Now this one's forced. There's only one place it can go. The bijective. So
No, it's factorials, now I understand.
right. That's the easiest thing that I can think of. Right? That's, by the way, what are you supposed to special about this function? Can anybody identify what is important about this? This
The
is it, this is the identity. That's where it's gonna be improved. Okay, so let's think about this. What else can I do and leave one alone? Well, I guess I can swap these two. So that's another one. Let's see, now I can leave two alone. And I can swap these two. Right? And following that pattern, I can leave three alone. Swap these two. Now, what these four that I've listed so far have in common is that at least one point is fixed, right? One here, two here, three here, and all of them here. What else can I do?
Probably shift left for them.
Right, you could do kind of a little shit. By the way, what do you suppose is the inverse of this?
So,
On the right. Good point.
These two are inverses. What's the inverse of this one?
Well, itself.
That is correct, because if you swap two things,
And so
you
again,
swap back, right? So let's call this, let's see, what would happen if I did, we call this F1, F2, F3, F4, F5. What happens if I do F4, F? I'm gonna close it in this order. Well. This would be F4, or I'm sorry, F3. So I'm gonna go this way, because remember, I'm composing the function. I'm gonna do this one first and this one. F3 is this rule here. And F4 is this rule here. So what happens? What's the sum total? Sum by what choice of work? What happens here when I do this composition? Where does one go? It goes to two and then on three, so it does that. Right? Where does two go? It goes back to itself. And three better go to one if this is a group, but it's always good to check, old Jim. Three goes to three to one. Okay, good. So this turns out to be F2. Agree? What happens if I run this in the other order? On the other hand, let's look at F3. So now we're going to do the F4 first in composition. It's the F4. What happens here? Where does one go? It goes to itself, doesn't it? So already I know these two things are different. Right, let's follow the rest of it. Two goes to three. And three better go to two, and it does. And this is in fact F1, isn't it? So notice this group is finite because, well, first of all, it's a group. If you compose any two bijections, you get a bijection, so that's good. Everything has all three of these. Well, actually, all four of these are their own inverse. These two are inverses of each other, and function compositions associated. So we're good to go here. This is a finite, non-abelian group. Everybody okay with me? By the way, this is the smallest. Fine, every group of order less than 6 has to be paid. Yes,
Is, F4, can you do that 3 times and that also affect the idea?
that is correct, but what that means is F4 squared is F5.
Right.
Since the smallest finite or the smallest finite non-abelian.
Did I say small finite? You're absolutely right. Let me make clear. This is the smallest finite non-abelian group. That is correct. Anything of order 5 or less actually has to be abelian. Anybody know another one? How many of you ever played around with one of these?
Well, I have, like, I've killed, still trying to solve my, it has the boy version, which has to have the center bits, you know?
This is a group under function composition, right? Because what happens when I move aside, call that X, call this Y, this is XY. Everybody agree with that?
Yes.
And notice, whatever I do, under function composition, and the function is whatever my hands do to this, I have this group of rearrangements for Rubik's Cube. Now, I don't know much, but I know this has to be finite, because if I get a pair of pliers and take this apart, there's
Yeah.
only so many ways I can put this back together.
There's a finite
Right.
combination, there's finite amount of elements.
Well, in fact, if you put this back together, if you take this apart with a screwdriver and take it apart, and you put, and all of a sudden you go blind for your sinfulness of taking apart this beautiful toy, and you put it back together blind, there's only a 1 in 12 chance that you can solve the cube after that without taking it apart again. So if you ever cheat that way, be sure to put it back in the solid position. But there's an enormous number of elements of this group, enormous number of rearrangements. It's like 4.3 times 10 to the 19th, right? It's huge. But it is a group, right? And it's fine. The operation, what happens when I do a rearrangement and then I do another rearrangement? I get a bigger rearrangement. Everybody agree with that? So it's got closure, a binary operation. Okay. What's the, it's associative because what I'm doing is a function and function composition is associative.
Yeah.
That's from 3190. What's the identity? Here, let me show you the identity. Don't touch it, right? It's the thing that leaves it alone, right? And does every rearrangement on the Rubik's Cube have an inverse?
Yeah.
Certainly. Imagine that you
Yeah,
got this out of the box, all
function.
pristine and new, and your little brother took it and messed with it forever and ever. And then
There's an
essentially
actual
someday you
sequence.
solve it. That's basically inverting, right? Getting it back to the original
Trying
state.
to find the reverse the sequence.
How many of you can solve
But I tried, but I
it?
failed.
It's hard. It's hard enough. Here's one of the reasons. This group is not abelian. Let's call this X. And let's call this Y. X, Y. See what that looks like. Y, X. Is it the same thing? It is not. And that is why when you try to do what comes naturally, solving this thing, it's more complicated. Because this is actually a finite, or the group rearrangements on this thing is a finite non-abelian group. Now, why do we study groups? Why? So we've got this thing, we've got some nice examples. In a certain sense, groups are the study of symmetry, right? I mean, when I was an undergraduate, even people in chemistry had to be exposed to some group theory because they were interested in, for example, lattice structures on crystals and molecules, things like this. Let me ask you a question, build your intuition. Let's suppose I do something with this cube. Right, just do a rearrangement, anything I want, I'll make it simple. If I repeat that, whatever I do to the cube, will it ever come back to being solved? Let me try an easy example. What if I do this? Well, let's do this, and again, and again, and again. There you go. Well, what if I do something more complicated, like this, my XY, and I do it again, and I do it again, and again, and again? So my question is, will this thing ever come back again? right? Like it did in the easy exam. What do you think? How many of you think it will? Okay, some people think it will. How many of you think it will not? Right, it does seem like, I might be in kind of an eddy, right? So notice every often I get that green cross. And every so often I seem to get the corners. But, you know, it's not really clear to me that I might not be stuck in some kind of eddy just going round and round in a circle. Anybody want to justify why they think that maybe it does come back? Want to throw in the two?
Well, it's probably a finite set, so doing it eventually will make it come back.
But, right, but my question is, how do I know that I'm not repeating? So how do I know that right now, this is the same thing that I got, you know, after the 20th move, and I'm just gonna keep going round and round in circles all the time? How do you get around that?
That would imply that the two actions that you're doing have some sort of inverse. And
Well, that answers the question.
See what I mean? If you want to come back to one of this.
It turns out that no matter what move you do on the cue, it will always come back to the soft tip. Right? If you start with a soft cue, you need to repeat something over and over. Right? Why? Because of the group theoretic properties, symmetry and structure. In fact, what happens here is because every element has an inverse, that conclusion is forced. In fact, actually, it's so kind of a little piece of trivia about the Rubik's Cube is the move that I just did, that 2-move thing. I had to do that 105 times for this to come back. The longest move on the cube takes 1,260 times. And if you think that's big, it is a bargain compared to the size of the Earth. So let me give you your first theorem. Now that we've covered some.
I might actually try that on my own, or maybe ski back at home. Give you how I crawled it and then chill it.
All right. 215. Let you deeper. So Braden can we can sort of say that you were the prophet for the day. Okay, first of all, in a group, the identity is unique. So the group says an identity must exist. This theorem says, okay, but there's only one of them. 2, for all A and G, A inverse in G. That was the one that you were talking about earlier. The inverse of any element is unique. Number C, A inverse. Anybody want to guess what this one is?
Hey, it's a. There's the service. Look at this, I didn't post it, and then. Inverse person.
Anybody want to guess what this one is? Be careful. Good. You probably saw something like this in linear algebra. Where the order is reversed. Or
That's all right.
Since you gotta be super careful. It's very tempting to write A inverse B, and that only holds if G is an abelian group.
or you're in trivial group.
But that's all it's doing. Yes,
I don't think it makes sense. Is the unique inverse? Is it part of the definition of group or is it a result of the?
it's a result.
Okay,
The group assumption is the inverse exists. The theorem says, hey, there's only one. All right.
okay.
You don't assume it exists. You get that kind of free. So, and I'll prove it.
No.
Suppose I've got two of them. E1, E2. Since E1 is an identity. But E1, E2 is E1. Since E2 is not identity,
One equals E2.
so E1. I mean, that's, I almost feel like you have to take a shot at that.
Trivial.
Feels like yeah, it seems.
Like I said, it's trivial, that's why, I said in my linear analysis class. I guess maybe it's a gradual course and for ours will not to be trifling with here.
So how about this one? This one I think is sort of simple. Let A be, and suppose B and C are inverses. Alright. This means that AB equals BA is the identity and AC CA. So how do we proceed?
Well, you probably say that AB equals BA equals CA equals AC.
I'll go a little slower.
We're gonna do.
Spread you out. Right. Now, what I'm gonna do is I'm gonna multiply this equation by C. Right. Now I'm gonna use the associative property. And of course, this is just C because the identity is the identity, right? And what is CA? It's the identity. Identities. So any two inverses are the same. Am I okay with it? Yes,
This is, I don't know if this makes sense. I feel, you talked about abelian versus non-abelian, but you multiplied by C on the left.
the assumption on the inverse though, inverse multiplies on both sides.
Okay,
If you look back in the group, when two things are inverse, it doesn't matter what order.
okay.
Okay, number C. And again, it doesn't matter what order because they're inverses. Right. So A is an inverse to A inverse. But inverses are unique. A acts like an inverse to A inverse, but there's only one inverse to A inverse. So A has to be A inverse inverse. Okay. I'll leave that last one for an exercise. I think it's a pretty good idea to try to show that. So let me recall for you a definition of order. So, here. I said, or about, I'll formula write this down here, definitions. Let G be agree. The order of G is this. And this is the cardinality. Of the underlying set. Remember, G is a non-empty set before we consider the binary operation on it. And so when I talk about the order of the group, that's just, hey, how many elements are there in this? This can of course be infinite or it could be finite.
So this correct, when you use the vertical line with the set, you're using that to denote cardinality.
That is correct. So for example, this is our early example of the bijective functions from the set 1, 2, 3 to itself. There were 6 functions in that. By the way, notice these are 2 very different groups. They both have 6 elements. This one is a billion, and this one was not a billion. Uh, So that's a big group. I sometimes, I usually will make no distinction between the different sizes of infinity. So the integers is an infinite group, the real numbers is an infinite group. You probably know from 3190 that the infinity of the integers is smaller than the one reals. I will usually not make that distinction, and if I need to, I'll make it clear. Let me give you this definition. In this situation here, we have G being a group. So this may, don't let this confuse you because I'm going to use the same terminology. I've defined over there the order of the group. That's just how big the set is. I'm going to define something called the order of an element in the group, which looks like it's something totally different, but it's intimately related. Okay, take your favorite group B and pick an element out of it, call it A. Number 1, yeah, so I will use this, this notation on this, but in some books you can see this, although it's kind of usually sort of an older or it's an older kind of notation thing. And let me make this. Part of A is the smallest natural number, and by natural number, I mean something positive, can't be 0. Such that when I combine A with itself n times, so this is a shortcut notation, which is combining A with itself using the group operation n times, you get the identity. And the order of A is infinity if no such n exists. I've got a second part of this definition, but let me do a quick example here. In Z6, the order of one bar is, how many times do I got to combine one bar with itself to get the identity? 6. One bar plus one bar plus one bar plus one bar. What's the smallest number of times I can do that to get the 0, which is 6? This is 6. What's the order of two bar? What was it?
3.
Agreed. What is the order of three bar? Right. What's the order of Z6? How many elements are in Z6? You notice the connection between these numbers and this one? By the way, here, I'll put one more number in there. What's the order of the identity?
Those are all the factors on.
That is correct. These numbers all divide this one. Should we dismiss that as a coincidence? I think not. What about this? No, Z6, Z. What is the order of one? Infinity. You can never add one to itself enough times to get 0, right? So the order of this element here is infinity because there is no such number. Remember my Rubik's Cube example? The order of this is 105. That's how many times I had to do that little swapping thing to get back. Yes.
So since those are factors of the thing, if you have a finite group, then do all of the elements have to have a finite order?
So your question is, if you have a finite group, does every element in that group have to have a finite order?
Yes.
That's a great question. The answer to your question is yes. And just for bonus, you can prove that on the next homework, right? You'll actually see that. But that is why my Rubik's Cube trick works, as a matter of fact, because of that statement that you pointed. Number 2. The exponent of G. And I'll use the notation EXPG is smallest n in the natural numbers such that x to the n is equal to the identity for all x. Again, there's no guarantee that the exponent of this exists. But if it does, so this is like this is the smallest integer such that when you combine any element group with itself n times, you get the identity. The exponent of Z6 is also 6. All right, in this particular case. Okay, any questions on? Let me get some here. Let me point out that the exponent does not have to equal the order of the group, right? this is something that there will be a consequence of some things that we'll prove later. It turns out the exponent of G is less than or equal to how many elements are in G. And here I gave you two examples where you've got equality. See if you can build a group where the exponent is actually smaller than the size of it. Yes,
6, like, if zero, like, or zero bar can like. Just go back after 1, like, why is it not 1?
because it has to work for every element, of the group,
Oh, okay.
right? Not just zero. Okay, other questions? All right, well, you guys cogitate this and we will see you on Friday.